All right, so yesterday we were doing conformational analysis of alkanes. Today we're going to be doing something similar. We're going to be doing conformational analysis of cyclohexane. So let's think about what cyclohexane looks like. We'll first start with the bond line formula. It's 6 carbon. So we can draw it just like this. And I brought my trusty model kit. So you guys can see that I've got 6 carbons aligned in a chain, right? What we need to do is connect them in a ring. So I'm going to add this extra bond. And we're going to attach it here and here. And what you may notice is it's pretty hard to get the model kit perfectly flat, right? It doesn't like being in that position. Instead, it wants to adopt kind of a staggered conformation, just like we saw yesterday. So let's imagine drawing this using Newman projections. And what I'm going to do is have 2 separate sets of eyeballs. We're going to have one eyeball looking down this bond. And we're going to have another eyeball looking down this bond. And we'll try to draw a Newman projection for this. So on one side, we will have a hydrogen sticking out, another one sticking up. And then bear with me as I fill this out. All right, so that's kind of the front approach, right? So can you guys imagine if you're looking at it, the front carbon's kind of puckered down. Can you guys see that? So we've got a CH2 pointed down. We're looking along these parallel bonds. And then the back carbon, if you look at it, I've got it actually puckered up a little bit. So we need to finish our Newman projection for the back carbons. So we've got a CH2 kind of puckered up in the back. And there we go. We can draw our Newman projection for cyclohexane. The CH2 is in the back, puckered up. This one's in the front, puckered down. What are the angles between each of these? Yeah, that's the weird thing with Newman projections is we also have to account for the fact that each of the carbons in here is sp3. So the angles are going to be 109.5. We can't get it to lay perfectly flat without going through that eclipsed conformation, which we said is really energetically unstable. And so it really prefers to form that staggered conformation where you've got one side puckered up and the other side puckered down. That staggered conformation is much more stable than the eclipse conformation. The reality is most people don't like drawing the Newman structure for chairs. It gets complicated pretty quickly, right? So I'm going to show you guys a new drawing technique today. So I'm going to show you how to draw a bond line, and I call this a chair. Your book also refers to it as a chair. So the first thing you need to do when you're drawing a chair is to draw 2 parallel lines that are kind of diagonal and offset. So draw 2 offset parallel lines at 60-degree angles. So what I mean by that is draw a parallel line set like this, and that's roughly 60 degrees, right? Easy enough. Number 2 is draw triangle ends. above and below to connect. All right, so let's redraw these parallel lines down there, and I'll show you what I mean by that. So we've got our two 60-degree parallel lines. Now in blue, I'm going to draw a triangle pointed down like that, and a triangle pointed up like that. You guys kind of see that? So we can even draw a dash right there, kind of showing our triangle. The one key thing to note is that you want to try to draw it so that your bonds are parallel to one another. So we already had our first set of parallel lines, right? Our 60-degree angles that were offset, and then we've got our triangles here and here, and then here and here. What I mean by that is, you see how this red one is perpendicular with that red one? And then we've got our blue one right there that's perpendicular with this blue one right there. And then last but not least, we've got this green one that ideally these should be perpendicular as well. So you want to try to draw your chair structure as best as possible. It takes a lot of practice to get good at.
What is the drop S-E?
Oh, that's supposed to be a SO. Sorry. That's S-O. There we go. All right. Now what we want to do is add substituents. Because each of those carbons is assumed to have hydrogens coming off of it, right? We don't have them drawn in now, so we need to draw in those hydrogens. So let's first draw straight up hydrogens. So first thing you want to do is add bonds straight up for carbons pointing up. All right, so let's draw our chair again really quick. Oh, let me do this better. I can do better. So if we think about the carbons pointing up, we've got one carbon here that's pointed up, one carbon here that's pointed up, one carbon there that's pointed up, right? So what we're going to do is draw lines straight up and down from those red carbons. And I'm going to add in an A to each of these. All right? Pretty straightforward, right? All right, now we want to add bonds straight down for the carbons pointing down. Oops. All right, so you can just add on to your structure. I'm going to copy this down here. There we go, paste. All right, so if we think about our carbons that are pointed down, we can label these in blue. We've got a carbon in the back pointed down, a carbon right there pointed down, and a carbon right there pointed down. So I'm going to draw straight up and down. You can see how that back one is actually behind this front bond, so I'm going to try to cut off a little bit to show that perspective. And again, we're going to label these up and down pieces right here, here, and here. So can you guys kind of see that? Let's take a break right now, and I'm going to pull out my model kit and show you exactly what I mean. So you see the carbon kind of pointed towards you guys is pointed up. I'm going to add in green for the ducks pointed up. This carbon's pointed down, so I'm going to put green pointed down. Next carbon's pointed up, so I'm going to put a straight up and down piece. Next carbon's pointed down, so I'm going to put it down. So on around the ring. There we go. We've got 3 pointed up and the 3 pointed down. They're completely vertical up and down. But then we've got these remaining positions for the carbons, right? We've got to fill in those hydrogens. So that's what we're going to add in next. So let's continue on. Number 3 is add last substituent parallel to adjacent carbon bonds. All right. So I'm going to copy this. You guys can just add on to the structure that you have drawn on the page. Paste this down here. Oop, I lost my A. All right, so let's imagine we now have a substituent coming off this way, and I'm going to label this as E. But can you see how this bond, I'm going to even label it in green, right there, is adjacent to this bond in the back? They're perfectly aligned to one another. That's what I mean when I say adjacent. You want it to be lined up so that they're parallel to one another. If we go and we keep on adding these in, we've got this one kind of sticking up right there, and I'm going to label this with an E. And again, you can see that this bond between there and there is now parallel to that bond between there and there. So we've got those adjacent. Let's keep on adding these in. We'll switch over to the other side. Add in this one, and then I'll do my best right there, and that one. We've got E and E. Those are adjacent to the bonds right behind them. And then we're missing our last 2 protons. So in the back, what we can do is draw one. Whoops, let me switch markers. We'll draw one out like that, and we'll draw one out like this. There we go. You guys are going to become excellent artists after this class. So we've got these straight up and down. Let's add in our additional protons. I'm going to pop in these bonds, but I'm going to use a different color, kind of like they're a different color on there. And here we go. So on my model that I'm showing you guys, the green ones are sticking straight up and down, and can you see how the yellow ones are kind of sticking out and away? So we've got different types of protons on our cyclohexane. The ones that are sticking straight up and down are referred to as axial. And then the ones pointed away are called equatorial. All right. Some people get confused with why we call this a chair. The way I like to think about this is like a chase lounge. You guys are familiar with chase lounges, right? On your chase lounge, you've got a part for your back that's kind of tilted up so that your head's pointed up a little bit. And then your torso or legs are kind of flat, and then where your ankles and feet are is pointed down. The same thing's true with the chair. So do you see how on one side, we've got a side pointed up? That'd be like our headrest on our chase lounge. then we've got kind of this square flat area, and then we've got our little area for our feet. So we call this a chair. Yep.
What is the green one that you give a label? The E there?
I was just showing, so these green bonds, it's showing that they're aligned, that they're parallel. So that's the way you want to draw them, is parallel.
So you're just kind of like marking.
Yeah, I was just trying to mark up those bonds. All right. So you guys ready to have your minds blown? Yeah? All right. Let's take a look at our chair. What if we flip our footrest on our chaise lounge up and turn it into a headrest? And what if we take our footrest, our headrest and flip it down into a footrest? Watch the axial positions, the ones sticking straight up and down. Ah.
Wait, do it again.
Let's do it again. All right, so now these ones are axial. The yellow ones on my model kit. Let's flip it. I'm going to put the footrest up, the headrest down.
It's like a rewind.
Yeah. So do you guys notice you can flip the axial substituents into the equatorial position? It's really strange, but it makes sense if you have a model and you grab your headrest and your footrest, pull your headrest down, your footrest up, and voila, you can switch those from one conformation into another. Pretty crazy, huh? We're going to draw it. So I'll show you guys how I like to draw chair flips. All right, so we first have to draw our original chair. So I'm going to do 60 degrees, 60 degrees, add in my triangle up here and here, and my triangle, let me move this out a bit, here and here. There we go. So, like I said, you can kind of imagine these as hinges. This is our headrest. This is our footrest. And what I'm going to do, or what I was showing you guys, is you grab this carbon on your headrest. It's the top of your headrest. We're going to pull this down. You're going to grab this carbon on your footrest, and you're going to pull it up, right? So if you go through and you think about this, there's a back and forth. Oh man, it's been a while since I've drawn these. Let's make sure I can do this. There we go. So can you guys see how our footrest, which was on the right-hand side, went from being in the down position into the up position? And then this one's now in our down position. So if you remember, I said that, let's take our footrest, for example. We had one position coming straight off of there. We'll call that A. Let me actually move this. And then another one coming down here that was B. What position is A in now? Yeah, it's sticking straight up and down. So the A is going to be our axial substituent now. And then B is going to be sticking over here, and it's going to be equatorial. So that's really important to note. During a chair flip, your axial substituents become equatorial. Just like you guys saw when I grabbed the headrest and footrest, the colors switched. All right, so now what we need to do is we need to know how to interconvert between our two-dimensional bond line formula to this more three-dimensional perspective for our bond line chair. So let's practice this a little bit. So how do we go from a 2D bond line to a chair? So let's think about cyclohexane, and I'm going to give us an example. All right. This is our 2D structure. One methyl group I'm going to draw sticking up, so it's a wedge. The other one is going to be sticking down, so that's a dash. All right, so that's our two-dimensional head-on view. So it's just like if we're looking at this straight down. What we need to do now is kind of assess what's going on here. So the top CH3 is closer to our eye than the hydrogen attached to the carbon. It's important to remember on this carbon, on the ring, this carbon shown in red, that there's another assumed hydrogen there, right? And that hydrogen, in order for this to be tetrahedral, must be pointed backwards. So we can even go in and say, all right, we've got that little hidden hydrogen pointed back. So if we're doing the top-down view, the methyl group is closer to our eye than the hydrogen. Let's go to the other carbon. That means that in this position, we've got a hydrogen that's a wedge, right? So we can say, all right, this methyl group is further away from our eye than hydrogen. And just for the sake of clarity, let's number our carbons so that we don't lose track of what's going on. I'm going to say carbon 1, 2, 3, 4, 5, 6 in our ring. So if we were going to name this, what would we name it using our IUPAC rules?
1,2-dimethyl cyclohexane.
Yeah, 1,2-dimethyl cyclohexane. And we're going to come up with a little bit more descriptive naming terminology, but let's first draw the chair structure. So let's fill in our chair. Oops. Let me clean this up. There we go. You guys should get art credit for this. All right. So I'm going to go through and number our carbons in our chair. We've got carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. All right, so now let's imagine instead of our straight-on view, we've got an eye from the sky looking down. On carbon 1, should the methyl group be axial, or should it be equatorial if we're looking straight up and down at the molecule? So let's think about it. If I'm looking straight up and down, and carbon 1's closer to my eye, the methyl group is going to be sticking closer to my eye than the hydrogen pointed away. And so it's going to be axial, right? So I'm going to go ahead and draw this, this CH3 as axial, and then the hydrogen is a little bit further away from our eye. Does that make sense on carbon 1? All right, then carbon 2. We've got a CH3 group pointed further away from our eye. So should that be axial or equatorial? Let's think about it. Which is further away from our eye, the axial position or the equatorial position? I would say that this position is closer to our eyeball than this position, right? So if the CH3 is further away, that means the CH3 must also be axial in that position too. So we'll fill this in as CH3 and then H.
Wait, where's the
So let's actually do this with the model kit. I'm going to throw on some methyl groups here. Whoops. All right, we've got a methyl group on here. Got a methyl group on here. I'll add in our remaining hydrogens. So can you guys, let's see if we can get perspective on here. This is tough. There we go. Give me a minute. Alright, so this one's closer. Let me switch these. You need to film this? I embarrassed myself enough. Alright. So can you guys see how the top methyl is closer to your eye than the back methyl?
Yeah.
Alright. And then when we look at it in our chair structure, one is sticking up in the axial position, the other one's sticking down, right? So what we call this when we have groups on the opposite side is trans, because they're on opposite faces. So this is called trans 1,2-dimethyl cyclohexane. Right? You guys are like, sure, I trust you on that. It's good enough for me. All right, let's do the other one. And so I'm going to draw a line down here. What's that? It was trans. So can you see how this methyl group right here is on opposite sides of our molecule than that methyl group? So we call it trans.
Wait, what's the meaning of the trans again?
Trans means opposite sides. All right, let's think about another molecule, also closely related. We're going to do CH3 sticking up, H sticking back, and I'm going to have another CH3 sticking up, and then H sticking back. And again, let's number this. We'll go 1, 2, 3, 4, 5, 6. Now if we look at the methyl groups for our new molecule, are they closer to our eyes than the hydrogens or further away? Closer. So let's try to draw this with the chair again. All right. And then I'm going to go through and number these. I've got 1, 2, 3, 4, 5, 6. Carbon number 1 should have a methyl group sticking straight up and down, just like in the previous example. Now, if we look at carbon 2, is that going to be methyl, or is the methyl group going to be axial or equatorial? Equatorial, right? So now if we look at this methyl group, it's sticking more up here, and we draw this hydrogen down. All right. So what do you think it might be called if they're pointing in the same direction? Cis. Yeah. Same thing with human sexuality, right? Trans versus cis. If it's pointing in opposite directions, it would be trans. If it's pointing in the same directions, it's cis. So similar nomenclature. So these are both pointing up towards our eyes, and we would call this cis 1,2-dimethyl cyclohexane. All right, but we can do chair flips, right? So I've got our trans one here. What if we do a chair flip? We got to think about that. Yep.
I still can't see why, like the wedge and the dash, like why it's closer and why it's up and down.
Yeah, so let's take a look with our model. So the one on the left, we said the top methyl is pointed towards us. The back methyl is pointed away. This time what we're doing is we're taking this methyl. We're going to put it closer. We're going to have it away. So can you see how now, in relation to the hydrogen, the methyl group's coming closer to our eye, the hydrogen's pointing away.
Okay.
Right? So you can even try to flatten it out and you say, well, both of these methyls are pointed in the same direction.
So that's
Both
what
these hydrogens are pointing back. Yeah, that's what we're showing with the two-dimensional figure. Yep.
So with the share picture, the reason the hydrogen pointed down is to show the way, and when that filter is coming off at that angle, it's supposed to be like towards us.
Well, remember, we're trying to add some perspective here. So we're imagining looking straight up and down through this molecule. So if we're looking at carbon 1, the methyl group should be closer to our eye than that hydrogen. And if we're looking at carbon 2, the methyl group should be closer to our eye than that hydrogen. So using both of these perspectives, we can show those methyl groups are relatively closer to our eye than the attached hydrogens on there.
Are we looking from the back or from the top?
I mean, you can imagine looking from the top of the molecule or the bottom of the molecule. It really doesn't matter.
In this case.
Yeah, I normally imagine drawing it from the top-down view. I think it's easiest. So let's imagine doing a chair flip. So flip. And then we want to draw this one, and we'll say flip. Try drawing the chair structure for the flip. So let's think about it. Even before we draw it, let's start with the one on the left. I'll get the model drawn here. This is our chair structure. Both our methyl groups are axial. What happens if we do a chair flip? What will happen to the methyl groups? They'd both be equatorial, right? So let's try it. Wham. Now all of the green ones are up and down, they're axial. Our methyl groups are equatorial. You guys see that? So let's try drawing the chair structure with them both equatorial instead of axial. So we can also imagine, all right, we're going to use the hinges between 1 and 3 and 6 and 4. So now this is carbon 1, 2, 3, 4, 5, 6. So carbon 1 we said should be equatorial. It should have a methyl group. So that's going to stick out over here. And its attached proton will now be axial. So I'm going to draw it sticking straight up and down through there. Oh, that was a little off center. There we go. So its attached hydrogen is now axial. Carbon 2, the methyl group should be equatorial. And its attached hydrogen should be axial now. This is still trans 1,2-dimethyl cyclohexane. We've just drawn it in its flipped form. So it sometimes can be a little tough to see. Again, if you do the top-down view, you can still see that one methyl group is closer to our eye than the hydrogen. The other methyl group is further away from our eye than that hydrogen. So it's still trans 1,2-dimethyl cyclohexane. All right, let's kind of pause here and think about trans 1,2-dimethyl cyclohexane. We've got one chair structure where the methyl groups are sticking out in the equatorial position. And then we've got another chair structure where they're sticking straight up and down. Which one do you think is more stable? Think about it this way. These methyl groups are like helicopter blades. If it's a helicopter blade, they can feel these other axial protons. Right? Those protons do take up room. And so axial is actually less stable than equatorial. If we have this spinning way out here, it's much further away from the proton. So, what's that? They are closer to each other, but they're much more stable because they're not running into the protons. So we'll talk about this. Typically when you've got positions or substituents in an axial position that are big, it's considered destabilizing.
So could you go back to the axial? Is it because there's more protons?
Yeah, it's the bottom methyl group is interacting with those two axial protons sticking down. The top one is also interacting with those those two protons sticking out. So you've got a bunch of diaxial interactions. We typically call them 1,3 diaxial interactions because they're separated in space through 3 carbons.
So axial is more stable?
Axial is less stable. Equatorial, when you're pointing out and away, is more stable. Let's take a look at the cis version of this.
Does that mean that axial has more energy?
Axial is less stable. Just like yesterday we saw those energy diagrams, you'd have to go to a higher energy level to force something into the axial position. It doesn't like being there. It would rather be sticking out and away from things.
So axial does have higher energy?
It's higher energy or less stable. All right, let's do our other chair. Let me see if I can squeeze this on one page. We'll do our hinges again between 6 and 4 and 1 and 3. So we've got 6 and 4 and 1 and 3. So I'll label all these protons again. This is 1, 2, 3, 4, 5, and 6. In the 1 position, our methyl group is still equatorial. Our proton is still sticking straight up and down. And then in our 2 position, our methyl group is now axial. And our other proton is pointed away. So can you guys see how we flipped from our axial position to our equatorial position for each substituent? All right, let's try one more practice one. We're going to do another dimethyl cyclohexane. This time I've got a CH3 pointed up and another CH3 pointed up. And if we number this, we'd say 1, 2, 3, 4, 5, 6. Do you think this is going to be cis, meaning on the same side, or trans, meaning on the opposite side? Cis. Both methyl groups are pointed closer to our eyes, right? So this is going to be cis 1,3 dimethyl cyclohexane. Let's draw this in its chair conformation. So we can go through and we can fill out this chair right here, right here, right here. Oh, let me clean this up. All right. And again, I'm going to number my ring. I'm going to say, all right, this is 1, 2, 3, 4, 5, 6. All right, the methyl group coming off of carbon 1, is that going to be axial, sticking straight up and down, or equatorial? Axial. So we'll stick this one straight up and down. We got CH3. That means the assumed hydrogen there must be equatorial, right? All right, then if we think about carbon 3, on carbon 3, is that methyl group going to be axial or equatorial? Well, let's draw in our 2 substituents and then decide. So we could have one sticking straight up and down like that, or another one kind of sticking out and away. So the one going straight up and down is axial, the one sticking out and away is equatorial. Knowing that, is that methyl group going to be axial or equatorial? axial. It's going to be closer to our eye. Both of them are closer to our eye.
Close your eye.
So imagine we're looking straight down on top of this, right? You see how both methyl groups are closer to our eyeball than the respective hydrogens off those carbons? Same thing with the bond line formula. They're wedges, so they're sticking closer to our eye if we're looking down on top of the 2D structure. All right, so let's make a model for this. Do you think this is very stable?
No.
No, we've got two competing helicopter blades, almost like a Chinook helicopter, not happy with one another if they're both axial, right? They're spinning through space, they can feel each other. That is a 1,3 diaxial interaction. And just for the sake of argument, let's draw in all of our axial groups. And I'm almost got it. If we think about all of our axial groups, they're sticking straight up and down here, 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 through here, and then down there. So they're all the flagpole ones. It's very, very destabilizing when you have bulky groups in the axial position. And these are called 1,3 diaxial interactions. And these are destabilizing. Let's try to do a chair flip. All right, if we do a chair flip, are they both going to be axial anymore? No. Okay, so I'm going to number these again. This is now 1, 2, 3, 4, 5, 6. The carbon coming off of, or the methyl group coming off of carbon 1 is now going to be equatorial. And the proton coming off of it will be axial. And then if we look at carbon 3, its methyl group is also going to be equatorial, and its proton is going to be axial. So let's take our model where they're both diaxial, very unstable. We flip it. Now they're equatorial. They're sticking out further in space. Which one's more stable? Yeah, the second one, where they're sticking out in the equatorial position. This one still has diaxial interactions between the protons or the hydrogens that are sticking straight up and down. But hydrogen's pretty small. It's okay sticking in that axial position. So let's finish drawing in all of our groups just for fun. And let's see. This one has no 1,3 diaxial interactions. Therefore, it's more stable. So just like with ethane, with butane, I said that some of those Newman projections weren't as stable as others. Same thing's true for cyclohexane. You can flip them, but some of the conformations are inherently higher energy or less stable. All right, so what we're going to do from now until the end of class, which is 5 minutes from now, is try to work on this in-class cyclohexane activity. So try to get up with a partner. What I'll do is tomorrow afternoon, I will post the key on the class website and email you guys. And the problem of the day is closely related to this. So make sure that you understand this before you try to dive straight into the problem of the day.